Hello, my name is Arnold. In chemistry lab, we are tasked with growing alum crystals. This is the progress on the growth of the alum crystals after 14 days. While it's not very clear on video, I will show a photo of the alum crystals. So here's the photo of the alum crystals. There are about 9 crystals formed, with some of the diameters being as small as 1 millimeter and as large as 4 millimeters. And so you see these ones are bigger and some of them are smaller. And also when the crystals are growing, the crystals tend to form on already existing crystals due to intermolecular forces. So instead of forming small new crystals, the existing crystals get larger. Since the crystals are larger now, it is apparent that the crystals are not circles. Instead, they have straight edges that form different types of polygons. The individual crystals also tend to adhere to each other due to the intermolecular forces. Okay, so to calculate the theoretical yield of the product alum, we will first need to look at the equations for the chemical reactions. In the first reaction, we would need to determine if aluminum or hydroxide is the limiting reagent. We start with a 4 molar solution of potassium hydroxide and at 0.991 grams of aluminum foil. There are 15 milliliters of potassium hydroxide, and so there will be 0.2 moles of potassium hydroxide. Since potassium and hydroxide is presented in a 1-to-1 ratio in regards to the compound potassium hydroxide, there will also be 0.2 moles of hydroxide. By dividing the mass of aluminum by the molar mass of aluminum, we obtain 0.0367 moles of aluminum. In the equation, aluminum and hydroxide is in a 1-to-1 ratio. Aluminum would be the limiting reagent, so 0.0367 moles of aluminum would be used up, and 0.0367 moles of aluminate ion will be produced. So for reaction 2, 15 milliliters of 9 molar of sulfuric acid is used. Since we did not use the entire 25 milliliters of sulfuric acid for reaction 2. From the calculation, 15 milliliters of 9 molar sulfuric acid translates to 0.135 moles of sulfuric acid. Since we obtained 0.0367 moles of aluminate, and the ratio of sulfuric acid and aluminate in the equation is 1-to-1, aluminate would be the limiting reagent. We then obtain 0.0367 moles of aluminum hydroxide. Since the aluminate and aluminum hydroxide is presented in a 1-to-1 ratio. For reaction 3, 10 milliliters of 9 molar sulfuric acid is used, the remaining of the sulfuric acid. From this calculation, 0.09 moles of sulfuric acid is used up, from a calculation similar to in reaction 2, and we have 0.0367 moles of aluminum hydroxide obtained from the previous reaction. To find the limiting reagent, divide the number of moles of sulfuric acid by 3 and the number of moles of aluminum hydroxide by 2. Comparing these two numbers, aluminum hydroxide will be the limiting reagent with 0.01835 moles. Therefore, 0.01835 moles of aluminum sulfate would be produced, since 0.01835 moles correspond to the number of moles of a compound with a coefficient 1. For reaction 4, the number of aluminum atoms will be 0.0367 moles, and the number of sulfate compounds would be 0.05505 moles, found by multiplying this number by 3. In reaction 4, the ratio of aluminum and sulfate is 1 to 2, so 0.0367 moles divided by 1 is 0.0367 moles for the aluminum atom, and 0.05505 moles divided by 2 is 0.0275 moles of sulfate compounds. Sulfate would then be the limiting reagent in this case, and since 0.0275 moles correspond to the number of moles of compound with coefficient 1, 0.0275 moles multiplied by the molar mass of alum gives 13.058 grams of alum. The amount of aluminum contributing to alum is 0.0275 moles multiplied by the molar mass of aluminum, which gives 0.743 grams of aluminum. That is theoretically reasonable considering that we started out with 0.991 grams of aluminum. The actual yield of alum is 19.5272 grams and the theoretical yield of alum is 13.058 grams. So the experimental percent yield of alum is 19.572 grams divided by 13.058 grams multiplied by 100, which gives 149.89%. As for the explanation, the explanation for an experimental yield of more mass is that impurities are introduced during the experiment. The alum that is produced is not completely alum, but it contains other compounds that may be unintentionally introduced. It is possible that initially, other impurities were already present in the aluminum or potassium hydroxide. So the solution produced in reaction 1 contains dissolved substances that are not supposed to be part of the aluminate solution. The impurities will be present for reactions 2 to 4. As the different compounds of aluminum precipitated redissolve again, the impurity would still be there. In the end, alum and impurities are precipitated out together as the solubility of the solution is decreased by placing the solution in the ice bath. This would explain the inability of the solution to become clear when our lab group was heating the solution up on the hot plate. That is because the undissolved substances are impurities rather than aluminum hydroxide. Since about 6 grams of impurities are introduced, it is most likely due to a problem in the vacuum filtration between steps 1 and 2, and that our group might not have performed that technique correctly. Tune in for the next video on the growth of alum crystals. Thank you.